Dear students, yesterday we had discussed about the best approximation and we had discussed the definition of it as X an inner product space, E a subset of X, are taking two elements X and Y in X. So Y of E is said to be a best approximation from E to X if and only norm x minus y is less than or equal to norm of x minus z for every z in E. In that way we have defined. So y is the best approximation. And we have discussed one theorem too. That is X an inner product space. Three parts are the parts A, B and C. We are using these ideas to prove the present theorem. That is theorem number 2. Statement is that E be a non-empty closed convex subset of a Hilbert space H. Then for any x in H, there exists a unique best approximation from E to X. In particular, there is a unique element in E of minimal norm. You can take the proof of it. See the proof in detail. H is a Hilbert space, E a non-empty closed convex subset H, taking an element x in H. As usual, we are taking D as the distance of x from E. That is nothing but infim of norm of x minus y in such a way that y is an element of E. Of course, there is a sequence yn such that norm of x minus yn is tending to D as n tends to infinity. You can call it as equation star. You claim that yn is a Cauchy sequence. To prove that yn is a Cauchy sequence, of course, yn in E, ym in E, so that yn plus ym by 2 is again an element of E. So yn plus ym by 2 is an element of E for all nm element of n. You can write norm of x minus this new element yn plus ym by 2. Whatever that must be greater than or equal to D. Call it as equation number 1. Then we are using the parallelogram law. You know what is parallelogram law? 2 times norm of x plus y square. Norm of x plus y square plus norm of x minus y square is equal to 2 times norm of x square plus 2 times norm of y square. The same way, instead of x you take x minus yn, instead of y you take x minus ym, so that 2 times norm of x square plus 2 times norm of y square is replaced by 2 times norm of x minus yn square plus 2 times norm of x minus ym square is equal to, by parallelogram law, norm of x plus y square plus norm of x minus y square form. So here these two elements are x minus yn, other one is x minus ym. Their sum you are getting 2x minus yn plus ym. Of course, it's true. And whatever their difference, it is ym minus yn. So substituting in the parallelogram law, it is 2 times we have, instead of norm x, we are having norm of x minus yn square plus 2 times norm of y square. So that norm of x minus ym square is equal to norm of x plus y square. That is norm of 2x minus yn plus ym within brackets square plus norm of x minus y square. What are we having? Norm of ym minus yn square. So what does it mean? This implies, you check it, norm of yn minus ym square, which is same as norm of ym minus yn square. That term is taken from the right hand side. That is equal to 2 times norm of x minus yn square plus 2 times norm of x minus ym square minus this first term on the right hand side. That is norm of 2x minus yn plus ym square for every mn element of n. Here on substitution, see norm of x minus yn, norm of x minus ym, that everything 10 into d you have taken already. So that is 2d square plus 2d square minus other one again 2d. So 2d square. Ultimately 4d square minus 4d square is equal to 0. For sequence yn is a Cauchy sequence. So sequence yn converges to some y in H. Since H is a Hilbert space, Cauchy sequence is convergent. But we have a sequence yn is a sequence in E and E is closed in H. That implies y is an element of E. Now consider norm of x minus y. How to write in terms of yn? Limit n tending to infinity norm of x minus yn. That is equal to d by star, equation star. So distance of x from E or distance xe is same as norm of x minus y. That is, y is the best approximation from E. Since E is a convex set, the uniqueness of the best approximation holds. By the previous theorem, part B. Unique element in, no, that is the continuation. The other statement is so which is the unique element in E of minimal norm. It can be explained like this. Y in E is set to norm of 0 minus y less than or equal to norm of 0 minus z for every z in E, or norm of 0 minus y, that is norm y, less than or equal to norm of 0 minus z, that is norm z for every z in E. And that is about the theorem. Then we have new section, that is projection theorem and Rees representation theorem. So before proving projection theorem and Rees representation theorem, we had to go through certain definitions first. And the first definition, that is, we are taking E perp. What do you mean by E perp? That is orthogonal to E. The space which is orthogonal to E, it is taken as E to the power perp. E perp we can call, or which is orthogonal to E, you can call like that. Now what I am doing is I am calling this as E perp, P-E-R-P, perp. Let X be an inner product space and E subset or equal to X, and E perp is nothing but set of all y in X such that y orthogonal to X for every X in E, or set of all such y in X such that y is orthogonal to E itself, a space itself. And clearly E perp is a closed subspace of X. So you have to prove that it's a subspace of X. You have to prove that it is a closed subspace of X. For that, it's a subspace of X first part. You take two elements, x, y, E perp, and alpha is a scalar, alpha in K. Then alpha x plus y is in E perp, definitely. Let z in E. Consider inner product alpha x plus yz, that is alpha inner product xz plus inner product yz, that is alpha into 0, because one in E, other one in E perp, orthogonal. Alpha into 0 plus 0. Both x and y are in E perp. So inner product xz is 0, inner product yz is 0. So alpha into 0 plus 0, that's equal to 0. Or inner product alpha x plus yz, that is 0. Or alpha x plus y is orthogonal to z, or alpha x plus y is an element of E perp. That is, whenever x and y are in E perp, alpha x plus y is again in E perp, which shows that E perp is a subspace of X. You are taking xn in E perp, that is for every n in n, show that sequence xn converges to x in X. We prove that x in E perp. That is, our xn is an element of E perp. you take that xn, this sequence xn converges to xn xn, or you select xn in EPURB in such a way that sequence xn converges to xn xn, or we prove that x is in EPURB, that is this limit is again in EPURB, a sequence is taken, its limit again in EPURB, z choose z then we have inner product xn z is 0, inner product xn z is converging to inner product xz as n tends to infinity, because inner product is continuous and sequence xn converges to xn. That is our assumption. We have taken such that xn converges to xn x. Okay. So inner product xz is equal to 0 because inner product xn z is 0 for every n in n, or limit of inner product xn z is equal to 0. So we get inner product xz equal to 0 for all z in E, or x is an element of EPURB, or EPURB is closed. Thus EPURB is a closed subspace of X. Already proved it's a subspace. I get is a closed. It's a closed subspace of X. So next part is actually we take F equal to span closure. We take F equal to span of E closure. And clearly F is a subspace X. And we can prove that F perp is nothing but E perp. So take an element in EPURB, that is x, inner product xz equals 0 for every z in E, inner product xz equals 0 for all z in span E, definitely, inner product xz equal to 0 for all z in span E closure to, because if z is in span E closure, then the Rx is sequence zn in E, such that sequence zn converges to z in X, or inner product x zn equal to 0 for all n in n, or limit inner product x zn is equal to inner product xz is equal to 0. So we get inner product xz equals 0 for all z in f, or x in f perp, that is first one, that is E perp is subset or equal to f perp. On the other hand, when x is in f perp, inner product xz equals 0 for all z in f, inner product xz equal to 0 for all z in E. Reason C, E subset or equal to f, it implies f perp is subset or equal to E perp, or x is in E perp, or f perp is subset or equal to E perp. So we get E perp is equal to f perp from 1 and 2. Second and part, suppose X is a complete inner product space, F be a non-empty closed subspace X, then clearly F is a non-empty closed convex subset of X. By theorem, the previous theorem, it is, we have proved it in last class. We have for any x in X, there is a unique part B, there is a unique best approximation y in F, and x minus y is orthogonal to F. So you write, split it and write like that. You write x as y plus x minus y for y plus x minus y in F, x minus y in F perp, and clearly capital X is equal to F plus F perp. Take x in F intersection F perp, it is x in F and x in F perp, inner product x 0, x equals 0, that is F intersection F perp is nothing but z0. So from 3 we have x equal to f direct sum f perp. The direct sum of these two spaces, f and f perp, that is what x. For any x in X, you can element this as x equal to sum of these, that is y plus z, for y is in f and z is in f perp. And such y and z are unique. Uniqueness we have studied earlier. For suppose our x is uniqueness, we can prove here y dash z dash, two elements y dash in f, z dash in f, or x equal to y dash plus z dash, y plus z is y dash plus z dash, y minus y dash is z dash minus z. You see y dash in f, y minus y dash in f, because f is a subspace X, z is z dash in f perp, that is z minus z dash is in f perp, because f perp is a subspace X, or y minus y dash is equal to z minus z dash. It's an element of f intersection f for p. You are getting y minus y dash equal to 0 because you already taken 0 is z0. F intersection f dash is f for p is nothing but z0, or y minus y dash equal to 0, z minus z dash equal to 0, or y equal to y dash and z equal to z dash. Now x in x, so can you prove p square equal to p, that form? And if it is possible, call p as a projection. For that, at x in x, then we can write x equal to y plus z, or y in f and z in f per unique. Now define, taking a new function p from x to x by p of x equal to y. We have defined this as p of x equal to y. What is p square? You have to prove that p square equal to p. What is p square x? P square x is p of px. What is px? It's y, p of y. What is p of y? It's y. Y is taken as p of x. Because y is nothing but y can be written as y plus 0, where y is in f and 0 in f per. So ultimately p square equal to p. Very important, that part. And p is called a projection of x onto f. Here range of p is f and 0 space of p, that is zp, that is f perp, or x can be written as the direct sum of rp and zp, or rp is orthogonal to zp. P is called an orthogonal projection of x onto f.